Okay, so we're just going to write some notes about this, and then we're going to look at a counterexample for where we can't just join up a fixed point like this. So if we start around here, so basically there's a certain type of fixed point, and they're called hyperbolic fixed points. And these are the fixed points that we've been looking at already in nonlinear dynamical systems. So a hyperbolic fixed points are those which have a e to the ct in them in their analysis, so where c is a real number. So things like attractive fixed points, stable nodes, even unstable nodes where c is a positive real number, these are hyperbolic. Saddle points are hyperbolic. I nodes and saddle points. These are hyperbolic, and for all hyperbolic saddle points, we can linearize these around the fixed points, as we have been doing, and we can join or connect the flow accordingly. Now, this isn't going to be the case for all fixed points. Now, what fixed points have we looked at that I've left out from here? So we've looked at nodes and saddle points, but we've also looked at centers. So this part of the lecture is going to be all about the nonlinearities of centers. Now, centers are a little bit different, as we're going to see. We didn't have centers when we looked at dynamical systems in 1D. But we do have them in 2D. Obviously we can't have them in 1D because centers, remember, are elliptical cycles or elliptical orbits, and therefore we need 2 dimensions in order to realize them. So let's have a look at a similar example to the one that we've just done, but one which gives us a center. So let's say x dot is equal to minus y plus ax, and then x squared plus y squared. So it's similar in the fact that it's got a cubic nonlinearity in x, and y dot is x plus ay, also x squared plus y squared. And you can see in x squared plus y squared, these terms here, it's giving us a term which is immediately screaming out at us polar coordinates. So they're going to feature a bit later in this example, as you might expect. Okay, so the question is, where do we have fixed points? And so that's the first thing we want to do. So where do we have fixed points? Fixed points we get when it implies that x dot equals 0 and y dot equals 0. And so if you look at that you see that because x squared plus y squared is always positive, the only way that we're going to actually have a fixed point here is when x star y star is equal to 0, 0. Okay, so let's have a look at this particular fixed point. Are there any other fixed points in the system? I don't think so, but let's just look at this one, and we can return to that question a bit later. Okay, so then we're just going to follow the procedure that we did for the previous example. So in the previous example, remember, we had this system here, and what we did was we linearized around the fixed points, calculated the Jacobian, and then drew the phase space. So that's what we're going to do here. So fixed point is 0, 0, so we're going to calculate the Jacobian. So Jacobian is, and I always like to just write it up, dxf dyf. Is this something you'll need to know for any exams? Yes, you will. Jacobian is quite an easy thing to remember. I mean, it's all possibilities of differentiating in respect to the variables and the two functions that you have. So let's call this f and let's call this g. And this might not be given in the question, this is f and g, but then in order that it makes sense that this is f and the f that you're referring to here, it does make sense to actually define this function somewhere in the question. So let's do that. Okay, good. So what have we got as f and what have we got as g? Well, they're up there. So what's dx of f is going to be, well, it's a product, so it's going to be a x squared plus y squared plus 2ax squared. And what's dy of f is going to be just minus 1 plus 2axy dx of g. G is this one is the one I'm looking at. Dx of g is, well, this first term 1, and then it's just plus 2axy. And dyg is, well, it's a product, so differentiate the first thing in the product and multiply it by the second. Well, that looks like a g, doesn't it? Let's see if we can do that a bit better. And then add to that the first thing in the factor multiplied by the differential of the second. So we get that. And that's our Jacobian. Well, we're only evaluating it at one point, so let's just, rather than putting this long expression, let's just evaluate it at that point, which is 0, 0. And what we're going to find is that this is 0, this is going to be minus 1, this is going to be 1, and this is going to be 0 as well. Okay, so what have we got there? It means dy df and dx dg are the only non-zero ones. Well, that's dy df and dx dg, so it's the off-diagonal terms which are going to be non-zero. So then our Jacobian becomes j is equal to 0 minus 1, 1, 0. Okay, right, so now that we've linearized around this fixed point, we can use the methods of linear 2D dynamical systems. So we'd find what the eigenvalues are and the eigenvectors. I'm confident that you can find the eigenvalues and eigenvectors of this matrix. I think we've done examples like this before, so I'm just going to tell you what the eigenvalues and eigenvectors are. So the eigenvalues are going to be, well, they would obey the equation lambda squared plus 1 is equal to 0. So lambda is plus or minus I. So if lambda is equal to I, we get that the eigenvector is going to be I and 1. And again, you might, I always repeat this, but you might be used to normalizing eigenvectors, but because our general solution involves these vectors multiplied by constants, that's not something that we're going to have to do. So let's just press ahead, and for lambda is equal to minus I, we get that u is equal to minus I 1. Alright, so what's this? This is, what type of fixed point is it? Well, we've got imaginary eigenvalues. So remember, eigenvalues occur in e to the I, e to the lambda times t. Lambda is going to be I, so we're going to have e to the it, and that makes us think of cosines and sines. So we've got a centre. So 0, 0 is a centre. It's not an ellipse at this point, because to be an ellipse in the eigenvalues you'd need to have some real part. For example, if c here is greater than 0, this would give us something that is in-spiraling, and if we had a positive number here, it would be out-spiraling. But we don't have a real part, so it's just a centre. So therefore our solution, remember, in general our solution around a fixed point is c1u1 e to the lambda 1t plus c2 u2 e to the lambda 2t. So here we get that r, which for this system is xy, it's not equal to, in this case, this is for the linear case, but it's approximately equal to what we found, which is sine t cos t plus c2 minus cos t sine t. And we're not putting e to the it's in there because we know that x and y are both positive. Sorry, they're both real, and so therefore we're writing the right hand side also in a manifestly real way, and we've written e to the it as as cos t plus I sine t, etc. And then, just so that this makes sense, this is for the linear case. It's definitely equal to that, but now in a non-linear case we can only say it's approximately equal to that, close to the fixed point. Right, so what we'd say is, okay, it's a centre, and depending on what our initial conditions are, we'll determine which way around we're going in the centre. But we've got a fixed point 0, 0, and if we were just naively saying that we could linearise and follow the rules, we've only got one fixed point that we're aware of in the system, and so we'd have something like this. The direction would depend upon the initial conditions. This is x and y. But this is the phase portrait, or the phase space. So these things in general, I should mention, are called phase portraits. So the shape that's made by the flow is called a phase portrait, and the space that it's in is called phase space. So I haven't mentioned that yet, but you might encounter that in the literature if you read any of the books. So the phase portrait is the flow, whereas the whole thing is phase space. But this is the phase portrait for when we have the linear system. Okay, let's try and get rid of that. That's good. Nope. For the linear system. And we'd expect it to change. We might expect it to change when we include these nonlinear terms. So the question is this correct? Is this the right phase portrait for the system that we're looking at? And the system that we're looking at, remember, is this one here. So we know that if we set a equal to 0, then we definitely get a centre, because we just have the linear system. But the point is that we have these extra non-linear terms. Do they alter the behaviour as we move further away from the linear point? Because remember that because we're in the when we linearise, we're assuming these things. Now we can go further away from the centre, so that these conditions are no longer fulfilled, and therefore the Taylor expansion that we did in order to derive the Jacobian, etc., is no longer valid, and we have to include higher order terms, or maybe we have to include all of the terms, and we can't just Taylor expand and make an approximation. So, are we in that situation or not? Well, the point is that for this system that we're looking at, we can actually do better. And what we're going to do is we're going to analyse this system in polar coordinates. Right, so I'm going to go all the way back down to here. So let's see if we can find a suitable colour. So we can do better. Okay, so polars, which I should probably say at some point, polars. Consider polars. X squared plus y squared is equal to r squared, and we've got one of these terms in each of our ODEs. Now, we've also got x dot and y dot, so I want to know how x dot and y dot look when I put them into polars. So what I can do is I can take this, which is the equation which defines the relationship between r and x and y, and there's a similar one between theta and x and y. Polars will use r and theta, and I can differentiate it to find out how these coordinates are related to the rate of change of x and the rate of change of y. So if we just differentiate both sides, we're going to get 2x dot plus 2y dot is equal to 2r dot, and I've cancelled the 2's. And you might say, okay, well, that's all well and good, but that doesn't really help us. But remember, we have an equation for x dot for this system, and that's the ODE that we're trying to solve. Remember, x dot is minus y plus ax, x squared plus y squared, and y dot is x plus a y, x squared plus y squared, and that's equal to r dot. And you can see that this system is quite nice because we've got a minus y here, which will, with the x form minus yx, and we've got a plus xy here, which together will form plus yx, and they'll cancel, and everything else is just going to be, well, okay, I'll write it out, just maybe it's easier just to write it out to see. So what we're going to have left is we're going to have ax to the 4 plus ay to the 4 plus 2a x squared y squared is equal to r dot. And if you look at that for a second or so, you can see it can be factorized, and you can see that we can get x squared plus y squared all squared times a is equal to r dot, but that's just ar to the 4 is r dot, so ar cubed is r dot, and that gives us an equation which we can solve really easily. It's an ODE. It's indeed nonlinear, but it's just in 1D. And you can solve that using methods. So what type of ODE is it? Well, you can view this as a first order separable ODE and use the methods that you learned there to solve it. You may know other methods, but we're not actually going to need to solve it because it tells us everything that we need to know. It tells us that if a is greater than 0, that r dot is greater than 0, because r is greater than 0, it's the polar coordinate. So we have a solution which spirals outwards. And if a is less than 0, then r dot is less than 0, so the radius is getting smaller each time, so we have a solution which spirals inwards. Okay, so you might go, okay, that's good. How do we know we're doing a spiral? What about a theta coordinate? Well, how is theta related to x and y in polars? We know that x is r cos theta, y is r sin theta, and we can eliminate r from these two equations by dividing one by the other, and we find that y over x is equal to tan theta. Now, you can differentiate both sides, and this gives you an equation. Theta dot is y dot x minus yx dot over r squared. Now I can imagine people in the audience going, well, how do you get that equation from the one that you just wrote down for tan theta? Well, that's a question on exercise sheet 3 of, it's question sheet 7, which we started last week, and you can show that. Right, so let's just accept that for now, and if you put in what y dot and x dot are in there, then you'll find that this is identically equal to 1, so theta dot is 1. Well, then that just means that theta increases linearly with time, so the spiral is just undergoing uniform rotation, so d theta by dt is 1. So if you wanted to, you could say, okay, theta is t plus a constant. Well, we don't have to do that. We can infer this from this. So in some ways we don't have to write down the actual solution, because the ODE is good enough. Right, so we've got something that spirals outwards and something that spirals inwards. And so what we actually have is not this at all, but we're going to have something spiraling outwards or spiraling inwards. So let's see if we can draw that. Better colour. So if a is greater than 0, for example, that basically what's happening is that you've got a, let's say we start here, it looks like it's going to be a circle, but due to these small non-linearities, let's say they're small, let's say A is very small, it doesn't quite meet. And so if you just have a small perturbation away from the system, so what do I mean by that? I mean, if A is really, really small, then it looks a little bit like the case for a circle. But if A is anything that isn't 0, then you can make it small as you like, but as this flow orbits around the fixed point, when it comes back to the original value of the polar coordinate theta, it's not quite going to join up again, because as it's gone all the way around, these non-linear terms, the ones that go like ax x squared plus y squared, ay x squared plus y squared, are going to have an effect such as to move it away from joining up. And so if it doesn't quite join up, then you get a spiral. And the effect gets larger as r gets larger. Okay, and it would be inwards. Just point the arrows in the opposite direction for a less than 0. And this is why centres are unstable. So they're called marginal cases. Marginal cases. Because yes, they're fixed points, but it's not like the flow is actually going into them at any case. So marginal cases are centres. Also higher order fixed points, which we're not going to cover, or we haven't covered, let's put it that way. I don't think we're going to cover them. What's a higher order fixed point? Well, we've got, imagine we had x dot is equal to minus x squared. Well, we can't linearize this because there is no linear term. So it would be a fixed point, but not only would x dot be equal to 0 at the fixed point, but x double dot is equal to 0 when we're at the fixed point, which happens to be 0. So that's a different type of fixed point. We're not going to look at those. We've only looked at fixed points that can be linearized. So if we added a cx here, then it can be linearized because it's got a linear term. Anyway, that's just an aside. So marginal cases like that are unstable to nonlinearities. I'm going to try and join this up now with what we did on Friday in the lab. So some of you got onto the plots, the stream plots. And so what we've got here is, this is a Python code, and you can see on the left hand side lines 24 and 25, we've basically put in the system that we have here. It's just that v is y, x is x, w and a are the derivatives, so w is x dot and a is y dot. And on the right I've plotted the phase portrait for when a is equal to 0.5, and you can see that things are spiraling outwards. So you can also investigate phase portraits, and it's really straightforward. Where you can see the code on the left hand side is really straightforward, right? I mean, okay, there's not that many lines of code is what I mean by that. So once you're able to plot one stream plot and figure out how it works, you can plot any other stream plots, and thereby have a visualization of 2D nonlinear dynamical system. So the thing to take away from this one is really that marginal cases like centers are unstable to nonlinearities, and you can't do a simple nonlinear analysis around them. So they're kind of the exception. Whereas when we looked over here, we had hyperbolic fixed points, which have something that go like e to the minus ct, where c is a real number. C can be positive or negative. So saddle points and nodes, and those ones are stable, and we can just join up the phase space as we did here. And that's the main thing to take from this podcast.